Welcome back to Differential Calculus. In this video, I just want to do a couple examples of some more challenging sort of optimization problems so we can see how it goes when things get a little harder. So let's get right down to it. We will start with a word problem, of course. So we're trying to design a box. We know how much volume it would have to enclose, and we know the cost for, it's different cost for the bottom and the sides, and we want to figure out how long and how tall it should be, like how long on the bottom, in order to make the smallest cost. Seems reasonable, right? So let's get right down to it. We've got some information here, and we want to turn that into a constraint and a function to be optimized. So what we want to do is first we want to say we want to optimize, and then I guess it would be the cost, right? Minimize the cost. So the cost would be, let's call it C. And what's that going to be? Well, I guess we need to maybe draw a picture. That seems right. Okay, so let's draw our box here, something like that. And let's say the bottom is a square, so both those are length x, and let's call the height y. So all of these would be y. And there's no top, right? So we just have the 5 sides at the bottom and then the 4 vertical sides. Okay, so the cost is going to be the area of each of those sides times the cost per centimeter squared of that side. So for the bottom, we're going to have 25 cents times the area, which is x squared. And for each of the sides, we're going to have 10 cents times the area of that side, which is x times y. And there's 4 of those, so we'll multiply that by 4. Okay, so if we clean that up, that is, of course, 25x squared plus 40xy. Okay, great cost function. Why not? Notice that it has an x and a y, so we can't just optimize it right away. We need some sort of constraint. So the constraint is going to be the volume. That is fixed. So our constraint, we actually have several constraints here, I guess. One is that the volume, which we know is going to be x squared y, length times width times height. That's going to be 32. And we also know that x has to be positive and y has to be positive. I don't want to look at putting in negative lengths or anything like that. And we could say x is greater than or equal to 0, but if x or y are 0, the volume is not going to equal 32. It would just be 0. So we can just say greater than. And notice that this is not, x and y are not defined on a closed bounded interval, so we're not going to be able to just plug in the endpoints or something like that. Okay, so like usual, what we want to do is we want to get our cost function to only involve one variable. And the way to do that is to take our constraint equation here, solve it for one variable, and then plug into the cost function. So to do that, so let's solve v. V equals 32. I guess we solve an equation. So that's going to say y equals 32 over x squared. And then we can plug into c. So c is going to be 25x squared plus 40x. And then instead of y, I can put in 32 over x squared. And now we have a function of x, and we can take the derivative, set it equal to 0, and all of that. So let's go ahead and do that. Let's clean up C a little bit. It's nice to simplify before you do derivatives. So we don't want to use the quotient rule or something, right? So let's say 40 times 32. I did already multiply that out. That is 1,280. And then divided by x squared times x is just over x. Okay? So that tells me that the derivative, now that I just have a function of x, I can say that's 50x. And then that's x to the minus 1 times 1280, so we're going to have minus 1 x to the minus 2, so minus 1280 over x squared. Then we set the derivative equal to 0. So I can actually multiply through by x squared here to get it out of the denominator. It's okay because I know x isn't 0, right? I mean, I'm dividing by x squared already. So I'm going to multiply everything by x squared, and then this is going to become 50x cubed. Well, that'll be 50x cubed. And then let's add the 1280 to the other side, so it equals 1280. Cancel some zeros, and then x cubed is 128 over 5. And of course, take a cube root. So x is going to be exactly 128 over 5 to the 1/3 power. And I did get a decimal for that too. I'm so prepared today. I got 2.947 centimeters. Okay, And then we want to find the cost of the box, so we also want to find y. So remember, y is 32 over x squared, so that's going to be over 2.947 squared, which is actually 128 over 5 to the 2/3 if you want to be all fancy. But I got 3.684. Okay, so these are probably the dimensions of the optimal box, but you should always check that the value you find is actually giving you a minimum, not a maximum or a critical point that's not a min or max. Oops. So to check this, oh yeah, we can check it now. So to check, I'm going to use the second derivative test. I've already got the first derivative right here. So I'm just going to take c double prime, and that's going to be pretty easy. So that 50x just becomes 50. Then I have 1280x to the minus 2, so that's going to be negative 2, which will be plus 2 times 1280 over x cubed. And of course, when x is positive, that's going to be greater than 0. Because we just have a positive number plus a positive number. We don't even have to plug in anything. We don't have to plug in the critical point if we don't want to. So that's positive, which means the graph is concave up, which tells me that we have a local min at 2.947. And the useful theorem tells me, because this is the only critical point, that this is a global min. So this is actually going to globally minimize, not just optimize, minimize the cost. And then we can just plug in. So we know c of x, that's 25x squared, that's this one up here. We can plug in 2.947 into there, and we're all done. So 2.947, I got 25 2.947 squared plus 1280 over 2.947. And I got $6.51, 651, and then that cents, so we'll convert it to dollars. And we're looking good. Oh, sorry, 6.51 if we make dollars there. So not so bad, right? So the setup is a little tricky maybe, but the point is you get a cost equation and a constraint. Your cost function probably has more variables than you'd like, so the constraint helps you reduce the number of variables. And because this is single variable calculus, every situation you're in, you're going to be able to reduce it to one somehow or other. So you want to get it down to a one variable function and then find the critical points, see if they're maxes or mins. Okay? Okay, so let's carry on here. In our next example, we've got a wire. So let me draw a picture of a wire. It looks like this. And it's 10 meters long. So let's say this is 0 and this is 10. And we're going to cut it into two pieces. One of those pieces will be bent into a square and the other to make a triangle. And we want to know how to have the area of the square plus the area of the triangle be as large as possible or be as small as possible. And I am going to say that we don't have to cut it. So we could use it all to make a square, or we could use it all to make a triangle. That way we're dealing with a closed interval instead of an open interval, and it's actually possible to answer this question. So the way I'm going to set it up is like this. Let's say we cut it somewhere like that. Let's call this distance x, and this distance y, and this is the wire we use for the square, and this is for the triangle. I don't know why I wrote out square and drew a triangle, but I did. Okay, so the area is what we want to optimize. And what's that going to be? So the side length of the square isn't going to be x, right? We're taking that x and we're dividing it into 4 equal pieces. So the side length is x over 4. Then the area is the side length squared. And then for the triangle, well, that's going to be a little trickier. So maybe we should draw that one. So we need a function for the area of the triangle here. Here's our triangle. Each side is going to be length y over 3. And now we need to know some trigonometry to understand how to find the area of a triangle like that. So what I'm going to do is I'm going to drop a perpendicular. I'm also going to remember that this angle right here is 60 degrees because the 3 angles are equal and they add up to 180. Okay, so now I actually have a 30, 60, 90 triangle. And we remember from trigonometry that if you have a 30, 60, 90 triangle, then the side across from the 60-degree angle is root 3 over 2 times the hypotenuse. Yes, that's one of the special triangles. So the short side would be 1/2 of the hypotenuse, and the long side, the long leg, is √3/2 times the hypotenuse. Okay, so good thing we all took trigonometry. And then the area of the triangle, of course, is 1/2 base times height. So it's 1/2. The base is y/3, and the height is going to be √3/2 times y/3. Okay, so adding those two areas together, we get the area enclosed by the square and the triangle. And that's the function we want to maximize or minimize. Okay, and then what's our constraint? Well, we have a few. Well, if you look at the picture, pretty clear x plus y equals 10, since we started with 10 total meters of wire. We also know that x is between 0 and 10, and y is between 0 and 10. Y is in the interval from 0 to 10. So we're not going to have one of them be 11 and the other one be -2 or something like that. Okay, and again, that just comes from physical considerations. But notice that x and y are in closed bounded intervals here, so if we find any critical point, we can just plug in the endpoints and the critical points, and that is the only places the min and max can occur. So let's carry on. I guess we better take the derivative, but oh no, we can't take the derivative. We have two variables. So let's solve the constraint, plug into the area equation, and then go from there. So I'm actually going to solve this for, what did I solve it for? I want all my numbers to match, so I have everything pre-computed. Yeah, let's solve that for x. Okay, so let's say x equals 10 minus y. So that means that the area function, just depending on x, is going to be 10 minus y squared over 4 squared, which is 16. And let's clean up this other part too. So in the denominator, we have 6 times 6 is 36. And the numerator, we have a √3 and a y squared. Okay, and just to make it a little easier, I'm going to note that 10 minus y squared is the same as y minus 10 squared. So if you square a negative number, you get the same thing as if you squared the positive number. So let's write that as y minus 10 squared over 16 plus this weird constant √3/36 y squared. Now I'm going to take the derivative, so I could multiply out the y minus 10 squared, but I know the chain rule, so I might as well just leave it like that, and the derivative's not as difficult. Okay, so I'm going to do, let's see, 2 times y minus 10 times the derivative of y minus 10, which is 1, still over 16, and then plus 2 times √3/36 times y. Okay, so of course we can cancel some stuff. The 2 and the 16 cancel and make a y minus 10 over 8. And then 2 over 36 is going to be √3 stays there, and the 36 becomes an 18. Y. Okay, great. So we are really trucking now. We have a linear function. We want to set this equal to 0, and you can probably tell there's going to be exactly one point where this happens, right? Because it's a line. So I guess I want to break up this fraction here. So that's going to be y over 8. And then I'll add the 10 over 8 to the other side. So then I have plus 3 over 18y. And add the 10 over 8 to the other side. It's 5/4. Something like that. It's looking good. So then y times 1/8 plus √3/18 is 5/4. Okay, so we just solved for y by dividing, and I'll spare you the details. Plug it into your calculator, and I get y is about 5.424. So notice there's only one critical point, and we're looking for a max and a min, so we actually have to plug in the endpoints too. So we're going to plug them into our function up here. So plug in 0 there, and I'll save you the gory details, but use your calculator. We get 6.25. That means 0 for the triangle and all of it for the square. We can plug in the other end, which means 10 for the triangle, none for the square. That comes out to be 4.81. Or we can plug in our middle here, 5.424. And I got that to be about 2.724. So that is clearly going to be the minimum, is if we cut it there, or the maximum is if we just make a square and no triangle. Okay? So another example for you. That is about all the time we have. So with that, I'll be done, and I'll see you in class.